Okay, thank you very much, Dima. And it's great to be here at this conference.
Misha, can you speak a little bit closer to the microphone? We can hear you very well.
Okay, let me check one. Just 1 second. Is it better now?
It's fine for me, but I don't know.
Yeah, we
Yes.
hear you.
You hear me? Okay, thank you very much.
But we don't see your screen yet.
Yeah.
Okay, it's fine.
Fine now. Okay, sorry. Okay, so what I would like to talk here is about the possible connection between the Planck scale and the electroweak scale and how all that can be related to conformal symmetry. Okay, so what I'm going to tell you about today is covered in few papers. This one, which is this year, and a couple of our other papers which were written a couple of years ago. Okay, so I'm going to start from motivations, from discussion of naturalness, and then I will come to discussion of possible non-perturbative semi-classical relation between the Fermi and Planck scale. And finally, it will be a conclusion. Okay, so first question is naturalness. Okay, so if you want to know what the naturalness is, the easiest way is to type this word in Google. And of course, Google will tell you what this is. There are different definitions. So one of them is that if we talk about something which is natural, then this is what is formed or existing in nature, related in nature, or the universe, etc., etc. If you want to know what unnatural is, you do the same thing. You put unnatural in your search engine, and you get that unnatural is something which is contrary to the laws or course of nature. Variance is what is normal or to be expected. Okay, and these are the interesting human definitions, of course. And so I'm going to pick up two of them. So natural is something which is existing or formed by nature, or based on state of things in nature, constituted by nature. And unnatural is something which is contrary to the laws or course of nature. Now we can come to particle physics and just to see whether this type of definition would work. So what is particle physics? Well, particle physics is perhaps, first of all, the standard model. And here we have a real triumph of standard model in particle physics. This theory is complete. The last particle, Higgs boson, predicted by the standard model, has been found. No significant deviations from the standard model have been observed. And with experimental values of the mass of the top quark and of the Higgs boson, the standard model is a self-consistent effective field theory all the way up to the Planck scale 10 to the 19 GeV. So in spite of this success, the standard model is condemned to be unnatural or fine-tuned, which is somewhat in the contrast with this definition, whereas the theories with low energy supersymmetry, composite Higgs boson, or large extra dimensions are profiting from being called natural. I would say that this looks to be unfair to unnatural standard model, since it describes the nature better than the natural theories. Okay, on more serious grounds, the naturalness in high energy theory is a rather technical criterion. So I think it can be formulated in the following way, that the physics at the electroweak scale, or right above it, should be organized in such a way that quadratic divergences in the Higgs boson mass are eliminated to remove sensitivity of the Higgs mass to physics at very high energy scales. And this statement is often represented in the following way. We have the mass of the Higgs boson, we do computations of corrections to the mass of the Higgs boson in the standard model. There is the main contribution coming from the top loop. Top quark loop is quadratically divergent, and so we can think that there is some new physics coming around right above the electroweak scale in such a way that the contribution of the standard model and of the new physics compensate each other, and there are no large contribution to the Higgs mass. Okay, so if we just talk about quadratic divergences in the standard model, then of course it doesn't make sense, because divergences, after all, is they're just associated with some tool which eventually disappears in renormalizable field theories. So we should better talk about some physics situation in which this new physics is specified in some way. And I believe that the origin of this natural requirement or hierarchy requirement comes about around 70s, coming from the paper by Gildener, who discussed gauge symmetry hierarchies. Okay, so from where the problem appeared? So the problem basically appeared after the grand unified theories of strong, weak, and electromagnetic interactions were designed. So this was more or less the first time in particle theory where very heavy particles came into the game. Okay, and so if you want to unify strong, weak, and electromagnetic interactions, then you put the standard model within the simple group. This group should be broken. It should be broken sufficiently strongly. The mass scale which appears there is about 10 to the 15 GeV. This mass scale comes about from quite a number of different considerations, such as gauge coupling unification. It's also required by phenomenological considerations, such as requirement for stability of matter and the long lifetime of the proton. Okay, so now we see that the theory which we have at hand, grand unified theory, it is a theory with two energy scales which are very widely separated. The mass of leptoquark divided by the mass of W boson square is a very large number, 10 to the 28. Okay, we can say, so what? Okay, so if it's a large number, maybe it's simply like that. So Gildener, what he said is that, okay, fine. Suppose that you fix this number in your Lagrangian in some way, you fix this hierarchy to be indeed 10 to the 28, but then you start to compute different radiative corrections to the Higgs mass, then you find out that you compute one loop, and if you fix this ratio to be this very large number, after computing one loop, you still have to tune your parameters with very high accuracy so that this ratio of the physical values is indeed so large. Okay, and if all these corrections are suppressed by alpha, then you find out that you have to make this tuning up to 14th order of perturbation theory, and that doesn't sound good. Okay, it seems that there is some artificial requirement. Okay, and to remove the sensitivity of the Higgs mass to this very large energy scale, say grand unification, is exactly the requirement of naturalness and the requirement of absence of quadratic divergences in the Higgs mass. And there were plenty of solutions proposed to solve this problem. For instance, low energy supersymmetry, where the compensation of bosonic loops is happening because of existence of fermionic loops, and if supersymmetry is broken at small energy scales, then this compensation works at low energies of the order of the big scale. Another possible solution is composite Higgs boson, new strong interactions. We can also consider large extra dimensions, which say that the fundamental scale of nature, such as the Planck scale, is in fact not as large as we think. So all this type of solution, they require new physics right above the Fermi scale, which was expected to show up already at lab, later at LHC, but this didn't happen. Oh, it has not happened until now. So that brings me to the point is that I believe that it's time to change the paradigm. Okay, so and here is a proposal how this paradigm may be changed. So if I go back, then we saw that the hierarchy problem appears when we consider two different physical scales. So the hierarchy problem doesn't make sense if we just consider the standard model not embedded to anywhere. Well, there may be a problem with Landau poles, but this is something non-perturbative. Okay, so what we've seen is that, at least in particle physics, new energy scale is associated with heavy particles. So if there are no heavy particles whatsoever, then these heavy particles do not show up in any loops, and therefore we shouldn't expect to have any large perturbative contributions. And so I would formulate another paradigm in the following way, that UV physics, and we do know that UV physics, which is not covered by the standard model, does exist. This is simply gravity, should be organized in such a way that the Fermi scale is much smaller than the Planck scale. Well, here an important remark is that the Planck mass is not a mass of any particle. Okay, this is just a strength of the interaction. And so, if you draw whatever diagrams in gravity, okay, gravity is not a normalizable theory, but still the particles which we have in gravity, graviton is absolutely massless, and the Planck scale never shows in any propagator of these diagrams. It just shows as a vertex. So there is certainly a problem because there is the gravity scale, and then there is electroweak scale. These two scales are very, very much different. Okay, the ratio between them is 10 to the 30 or so. And we can ask ourselves, are there any places or any other examples in physics where very large or what is the same, very small numbers may be coming from? And the answer is yes. Yes, we do know plenty of examples where small numbers appears. So there are examples associated with quantum tunneling. So for instance, if you consider the decay of heavy nuclei, alpha decay of uranium, for instance, then the decay rate is suppressed by the tunneling exponent. So alpha particle, when it goes out of the nucleus, it has to tunnel through some barrier. Okay, and that makes this process perturbatively impossible. We have to estimate this tunneling exponent, and then this is a small number. Yet another example, which is also associated with tunneling, which is also very well known, which appears already in one-dimensional quantum mechanics, is that if you have a double well potential and you consider the splitting between two energy levels in this quantum potential, then there is odd energy level, there is even energy level, and the difference between them is extremely small. It's suppressed by tunneling exponent, which describes tunneling from this point to that point. Tunneling doesn't cover, is not necessarily needed to get small numbers. Yet another example is the mass gap in the BCS superconductors, where the critical temperature is exponentially small in comparison with the device screening, which takes place in these superconductors. So, I mean, all these examples perhaps are telling us that there may be just one fundamental scale in nature in Planck, and that the electroweak scale is generated from it non-perturbatively. Okay, and if this is indeed a non-perturbative phenomenon, then we may expect a relationship like mh is equal to square is equal to m Planck square times exponential, and here we have some number, and if this number is about 80, then this difference between these two scales may be because of non-perturbative physics. Okay, so suppose we accept that. Well, now just in words, later I will show you an example where this hypothesis can be substantiated. Let's first decide what to do with the phenomenological challenges to this picture. So if we say that there is just the standard model, there is just gravity, then in this type of theory, there are no heavy, new heavy, relatively strongly interacting particles, such as lepton quarks. Then we can ask ourselves, the standard model is not complete, okay? So theoretically it's fine, but experimentally it's missing several pieces. It cannot explain origin of neutrino masses, there is no dark matter, baryon symmetry of the universe is not explained there, there is cosmological inflation. How do we do without any new stuff? Okay, so the answer is actually very simple. If you have new particles, which are relatively light but feebly interacting, then you are not introducing any hierarchy problem, but you can solve all these challenges which the standard model faces. And actually the simplest model which does all that for you as the standard model in which, in addition to left-handed neutrinos, right-handed neutrinos are introduced. And this theory, in this theory, the Higgs boson breaks electroweak symmetry, inflates the universe. The right-handed neutrino with the mass in KV region can play a role of dark matter. Two other right-handed neutrinos can give masses to neutrinos and produce baryon symmetry of the universe. So this theory is very much similar to the standard model. It doesn't introduce any new scales, and it doesn't have any phenomenological problems. So now let's come back to theory, and let's try to see what are the requirements we should impose to the theory so that non-perturbative generation of electroweak scale becomes possible. So first of all, perturbatively, we should have mass of the Higgs equal to 0. Okay, and this should come from some symmetry protection. Okay, so that we should have a theory in which if mass of the Higgs is put to 0, then we compute different corrections, and then this mass is not generated by perturbative correction. So why so? Because if it is generated by perturbative corrections, then it's unlikely to be exponentially small. Okay, the second requirement is the absence of super heavy particles coupled strongly to the Higgs boson. So why so? Then we are coming back to this naturalness argument. If there are these large particles, then we will get a situation like in grand unification, where contribution of these particles will generically bring the mass of the Higgs boson to the high energy scale. Okay, and then I'm talking about non-perturbative effects, and non-perturbative effects for me will be semi-classical effects. Okay, semi-classical meaning that there will be some configurations living in Euclidean space-time, which well, can be called instantons or something like that, which have sufficiently large action and which generate non-zero vacuum expectation value for the Higgs field. Okay, so let's go through these different points. First of all, symmetry protection. If you take a standalone standard model and put the mass of the Higgs boson to 0 in the standard model, then the classical Lagrangian has wider symmetry. And the classical Lagrangian is scale and conformally invariant. So if I talk about dilatations, global scale transformation, then this transformation change the coordinate, spatial coordinate x, and introduce some factor which is associated with canonical dimensions for all the fields of the theory. So the attractive features of classical scale invariant conformal theories is that there are no explicit mass parameters, only dimensionless couplings. Now, if you take this theory, then the radiative corrections generically generate a mass scale for the scalar particles. Okay, and this comes from a famous paper by Coleman and Weinberg, well, 50 years ago. So what happens there? So you start with a theory which is at the classical level as scale and conformally invariant. And then there is an intrinsic scale in this theory associated with the conformal anomaly, with the breaking of scale invariance due to dimensional transmutation, whatever you call it. The physical quantities which show up there, they depend on renormalization scale only logarithmically. no counter term is needed to renormalize the scalar mass. And this means that the Higgs or scalar mass can be predicted in this type of theory. So how do we see that at the level of RG equations? So if you write RG equation for the parameter, the scalar mass, then the derivative of the scalar mass is proportional to itself. Okay, so MH equal to 0 is a fixed point. And no counter term is needed for MH, and therefore MH can be computed. So how Coleman and Weinberg computed that? Okay, so they found the effective potential in this theory. Then you discover that the effective potential of this theory has a minimum at scalar field which is not equal to 0. You find this minimum, you find the Higgs mass, and this minimum, you find the W mass and this minimum, and what you determine in the ratio of the Higgs mass and W mass. Okay, and so that's a finite number, and it's expressed through the gauge coupling. Okay, this is very attractive mechanism, and of course many people worked on that, trying to get the Higgs mass out of this idea. Unfortunately, it doesn't work in the standard model. It happens that if the mass of the top quark is smaller than some critical mass, okay, and this critical mass is about the actual mass of the top quark, then the minimum of the effective potential is generated. It's not generated because of Coleman-Weinberg summation over loop diagrams. It's generated because of chiral symmetry breaking in QCD. However, the wave of the Higgs field in this case is about 100 MeV, which is very far from reality. Okay, so it's not good. Now, if you take that the top quark mass is larger than this critical value, then indeed Coleman-Weinberg phenomena does generate an extra minimum of the potential. Okay, but it happens that this extra minimum of the potential is generated at the scale which is exceeding the Planck scale. Okay, and therefore it also doesn't work. And so the idea fails. You can correct the idea by introducing new particles, new fermions, new scalars, but the trouble on this way is that we know that there is gravity, okay, and gravity comes with dimensional full parameter, which is the Planck scale, and therefore it must be taken into account. Okay, because it could be well that there are corrections just coming from gravity which completely invalidate this Coleman-Weinberg computation. Okay, so if we use perturbation theory and mass-independent regularization, such as dim-Greg, you find that there is no gravity contribution to the Higgs mass. So all corrections to the Higgs mass are suppressed by the Planck scale. And therefore, if gravity is included and we use perturbation theory, which respects maximally scale invariance, then we find that the fixed point at MH equal to 0 remains in force. Okay, so we don't need any counter term which corrects or which removes the divergences from the Higgs mass, and therefore, in this type of theory, the Higgs mass can be predictable. Okay, and so gravity plus conformally invariant standard model gives us an ideal playground for looking for non-perturbative generation of the weak scale. It's kind of amazing that the simplest theory may actually work. So what kind of simplest theory I have in mind? Let's take gravity plus the scalar field. Okay, and I take scalar field with non-minimal coupling to Palatini gravity. I will explain in a second why this is important. So the action looks like this. Okay, so there is a scalar curvature, there is the Planck mass, there is non-minimal coupling of the scalar field, and then there is a kinetic term for the scalar field and potential. Okay, so potential, we want to have a theory which is conformally invariant without gravity. So this potential is just the lambda 5 to the 4th, as we have it in the standard model. Okay, so just a couple of words what the Palatini gravity is. Palatini gravity, it is using the following structures. It uses metric, which define distances, and symmetric connection, which defines the parallel transports of the vectors. And in the Palatini gravity, these two entities, metric and symmetric connection, are considered as independent variables. Well, in the metric gravity, this guy is expressed through the metric. A remark: if there is no matter, Palatini gravity is exactly equivalent to Einstein gravity. Well, if matter is included, in particular the scalar field, this is not the case anymore. So it happens that if we have this parameter xi, which is sufficiently large, then this theory allows semi-classical treatment, at least in the domain we are interested in. And this happens to be not the case for the metric gravity. Okay, I will say a few words about that later on. Okay, so what do we do with this theory? We would like to compute the Higgs vacuum expectation value. Okay, and then I imagine that we include all fields into account. Okay, so I'm writing here dg mu, but integration over connection should be included as well. Okay, and S is the Euclidean action of the model. Here I should say a remark that Euclidean path integral for gravity is actually not well defined due to the problem with conformal factor of the metric. So it's not clear whether this expression really exists, but perhaps it can be understood as analytic continuation from Minkowski expression, as was discussed earlier during Jean-Luc talk. Okay, so if the scalar field is smaller than the Planck scale, then the gravity is irrelevant and no contribution to the vacuum expectation value of the Higgs field comes from the Higgs loops. So the challenge is to account for contributions with the value of the scalar field, which is greater than the Planck scale. So let's look at the theory in this domain. The theory in this domain, the Planck scale can be omitted, and we get this simple action. So this simple action, it has interesting properties. It is scale invariant, and the Planck scale, which appears there, is actually dynamical, and it depends on this parameter xi and the scalar field phi. Okay, and so the conjecture here, which can be checked a posteriori, and this check can be made, is that if phi is greater than m Planck over square root of xi, the path integral is better to be found in the Einstein frame. The connection between these two frames is the following. So what you do, you make a conformal transformation which puts the phi dependent Planck scale into the form which doesn't depend on the scalar field. Okay, so this definition can be done easily with the initial Lagrangian. So here is the phase and field transformation which appears there. Phi is the original field, and chi is a new field which brings the system in the Einstein frame. And here is the resulting action. Okay, so this is just the Planck, the normal gravity action. This is the canonical kinetic term for the new field, and this is the potential. So what is most important for me is that the field transformation defined here is extremely nonlinear. Okay, and it's actually phi field contains an exponent of the high field. And so when we make this transformation, then the phi field, the average of which we want to compute, is transformed into exponential function of the new field high. What does it mean? This means that when we formulate the saddle point principle for computing of this path integral, then we will have to search for the minimum of complete action and not only the original action which we used to have from the very beginning. Okay, and this means that equations of motion contains new terms, and this allows for new solutions, new classical solutions. Okay, so the influence of sources to computation is, in a sense, a generic thing. I mean, the simplest example is that if you consider the integral of this type when x goes from minus infinity to plus infinity, and if you take large n, then you have to modify your saddle point in order to get a correct result. Okay. After I sell all that, everything else is really technical details. So what you do, you say, okay, let me look for O4 symmetric metric. Take O4 symmetric metric. This is a new term which appears in the equation of motion for the scalar field. You impose appropriate boundary conditions. You ask yourself whether you got a semi-classical parameter in your action. So this is your total action, which contains the source term and everything else. You can find out rescaling of different fields, which takes away the factor square root of psi out of this integral, and everything else inside doesn't depend on parameter psi. So that tells you that indeed there is a semi-classical configuration. And that's it, okay? The life actually happens to be a little bit more complicated because the delta function singularity in equations of motion, in literally the theory which I'm considering, leads to divergences. Okay, and there are divergences associated with distances going to zero. It would be too naive to think that the Lagrangian which we wrote is an ultimate Lagrangian. And so what we can do, we can add to this action higher dimensional operators. We can require that these higher dimensional operators do not introduce new degrees of freedom and also do not spoil scale invariance when the scalar field is large. Okay, so that's an example of this operator. You take this example and then you find that everything works in a nice way. So what this picture shows, it shows the following. So this axis here is the logarithm of this parameter psi. Okay, so this is our semi-classical parameter, which we wanted to be large, so that semi-classical approximation works. This axis here is this parameter which we introduce here to parameterize higher dimensional operator. So the natural choice of this parameter is psi squared, because then all these terms which we introduce, they have the same UV cutoff M Planck divided by square root of psi. And so this line corresponds to the correct hierarchy. Okay, we cannot predict hierarchy because it depends on this unknown parameter psi, but we can find the values of psi which will give us the correct Higgs to the Planck scale ratio. Okay, so this is this line. Okay, now you can put other lines here. There is say this line. Okay, so this is constrained from inflation. So the same theory is also good for explaining why the universe is large, homogeneous, and isotropic. And this also requires sufficiently large values of psi. Okay, so the psi should be greater than 10 to the 6. Then there is a constraint coming from the top quark mass. We know what the top quark mass is with some accuracy. We want the value of scalar self-coupling to be positive at the scale of inflation, and this puts this upper bound. Okay, so within this square, everything works. Inflation works, and the electroweak scale is much smaller than the Planck scale. So I'm finished. One remark is that if you do the same in metric gravity, then this large parameter psi doesn't help, because it doesn't show up in any of the formula. So I'm coming to my conclusions. The first one is kind of the fact that the standard model is in the great shape experimentally. Perhaps its success is telling us that there is no new physics between the Fermi scale and the Planck scale, that the new physics is hiding below the Fermi scale. And the reason why the Fermi scale is much smaller than the Planck scale is rooted in conformal invariance of the standard model and the non-perturbative effects associated with gravity. I'm finished. Thank you very much for your attention.
Thank you. So please, questions. Yes, Elias first. Elias, we couldn't hear you.
I'm sorry. You mentioned that the gravitational corrections, basically you work with a regularization so that you don't get quadratic corrections to the mass of the Higgs. Now, if you do the same in the standard model, you would think there is no hierarchy problem. So I was wondering, why do you assume this from gravity?
I'm taking perturbative gravity. So I take the standard model and I add gravity to it. Okay.
Right.
And then I compute corrections to the Higgs mass. Okay. Mm-hmm. And of course, if you use dimensional regularization, then you know that the coupling constants appear polynomially, and therefore
there are no quadratic corrections.
Yeah, there are no quadratic corrections, and this is what I'm using here.
Right, but I understand. But on the other hand, the fact that in this particular regularization there are no quadratic corrections doesn't mean that the theory doesn't have quadratic corrections. It's just that you're using a regularization that doesn't see them. In fact, to see them, you have to look at poles at epsilon minus 2, for example, in that particular case. Because otherwise, we would also think that the standard model doesn't have a hierarchy problem just because we're working in dimensional regularization. The question is, how important is this for your argument?
Well, first of all, if we have standard model without any gravity, then there is no any hierarchy problem in this theory. Because
no, of course, no. But if you, if you add extra physics.
If you add extra physics, and if you add extra physics such as grand unification, then
Right.
then I do see that there are large corrections. Okay, even if I take dimensional regularization, I see that there are all these heavy particles appear in the loops, and then I will find large contributions to the Higgs mass. So there, yes, there is this type of problem. However, if I have gravity doesn't have any perturbative, at least. Okay, it has black holes, but I don't know how to compute the contribution of black holes into the Higgs mass. But if I'm staying in completely perturbative grounds, then there are no corrections to that. At least I can specify a way which is rooted into, if I require, okay, I do require that my theory respects scale invariance. Okay?
Right, but in a sense, it's like asking that your gravity theory doesn't have a cutoff.
The gravity theory is, well, that depends what we name as a cutoff. If the
a cutoff means a place where new physics has to happen.
The new physics has to happen. No, this is new physics has to happen. We decide by doing a different type of computation. The computation we are doing to find whether new physics happens or not, we consider, say, different scattering amplitudes, and we find the place where this scattering amplitudes hit the unitarity bound, which signals that the perturbation theory at this domain doesn't work.
Right, which usually you expect it to happen in that theory if you go to sufficiently high energy, right?
Exactly, and in this theory, this will certainly happen at the Planck scale, and moreover, in the theory which I'm considering there, that will certainly happen at the scale M Planck divided by square root of psi, because this non-minimal coupling introduces some extra scale for sure.
Right, but the theory at that particular scale is not perturbative anymore.
Yeah, theory is not perturbative.
Okay, thank you.
Is Norma.
Thank you. Thank you very much. The standard model is in grid shape. I completely agree. I would like to see why, I mean, but in the aim to extend the standard model for, I mean, as you know, neutrino masses and grand unified theory. I don't see here how do you find the grand unified scale, and why, I mean, which I think is very important from the point of view of particle physics, more than to have at this level gravity, because in any case, here you don't have a quantum theory of gravity. You have the Planck scale playing a role, but so that is one of the points. I have other two about the coupling side, how that is recognized as a semi-classical parameter, or which is the size, which is the number for that, in particular for the mass of the Higgs, which you have as M Planck square, I mean, in connection with the value of the action, of the Euclidean action. But that is, I mean, this is another point in your framework.
Okay, so let me start with the first part. What I was discussing here is the theory without any grand unification. And I myself, I don't think that grand unification is necessary. Moreover, we don't know whether it exists in nature or not. So this is our hypothesis. And yeah, let's make it simple. There is no grand unification. Okay? And concerning the second question, I'm not sure I got it about.
How do you compute the coupling psi, or how do you obtain? Because you mentioned constraints from the data.
Okay.
But from how do you compute it if you want to extract it in your framework?
Yeah. Okay, thank you very much. Okay, so the parameter xi, which appears in this in this Lagrangian, this non-minimal coupling, okay, a priori it's a free parameter. It's just free parameter. Okay, so no idea what this parameter could be. Now I'm saying, okay, I would like to change this parameter in some domain and see what kind of values of xi I should take in order to get hierarchy between the Planck scale and the electroweak scale. So I say that if I take xi of the order of 1, the weak scale and Planck scale will be of the same order. Okay, and this and in this way you can find out what kind of xi you have to take. And in this example, on this line, so this line, you can consider it as a phenomenological line. You say that I know what is the ratio of the Planck scale and the Higgs mass. This is some number. And along this line, this is reproduced. Okay, and then I see that the value of xi should be sufficiently large. And this is needed for self-consistency of my computations. But then there are other considerations which are absolutely not related to this one. And this other considerations could be inflation. Okay, so what is interesting about theories with non-minimal coupling of scalar field to gravity is that these theories naturally lead to inflation. But they only lead to successful inflation if parameter xi is in some domain, okay? And this happens to be this domain. And this is coming from phenomenology, okay? So this part is coming from relationship with covariant normalization of the amplitude of scalar fluctuations, and this comes from yet another requirement of positivity of the scalar scale.
I see, Michael. I don't want to take the time for others, but I would like to point out that in this framework for inflation, I mean, you constrain the size, but there is the inflaton is too light to reproduce all data for inflation. So
no, inflaton here inflaton is the Higgs field, and all everything is reproduced, and moreover the prediction.
Grand unification precisely, or the scale of grand unification is in the it's in the semi-classical gravity, and inflation is connected to that. So it's not as lowest as the Higgs for inflation.
Yeah, I'm just coming to my first point is that I'm dealing with a theory which doesn't have any grand unification. It's just a standard model plus gravity, nothing else.
Last question, Autumn.
Hi there, Misha. So I was just going to ask. So when you couple to gravity, you introduce this dimensionful coupling, the Planck mass, and so you're not trying in your scheme to maintain scale invariance when you couple to gravity. Have you tried that? And could you tell me whether what goes wrong if you try that?
Oh, it's okay. If you take literally this theory, and if you say that the Planck scale is equal to 0 there, then this theory contradicts the experiment. Okay, as simple as that.
Even if you.
Yeah, it contradicts the experiment because of the simple reason the Higgs mass in this theory would be equal to 0. Okay. Now, however,
what about adding terms that are quadratic in curvature? Does that change the story at all?
The terms which are quadratic in curvature, that does change the story in the following way. You get a new degree of freedom, which comes from our square gravity. However, this degree of freedom, it's also a scalar field, but this scalar field happens to be heavy, and it couples to the Higgs sufficiently stronger. And this invalidates one of my requests for this theory. Once I have some heavy scalar field which couples strongly to the Higgs, then the hierarchy problem is back. But still, one more remark along these lines. There is a scale invariant generalization of that. And this scale invariant generalization is one extra field. So what you do is that, well, instead of, yeah, okay, well, you can say that, okay, there's not a Planck mass, there is an extra scalar field gigaton, which has a wave and which gives which induces the Planck scale. Okay, so this theory is completely scale invariant, and everything what I said works in this theory.
And in that case, your story is just that theory, it's just expressing that theory in some particular conformal gauge where that dilaton is a constant. Yeah. Okay, thank you.
Okay, Francesca.
Thank you. I was wondering if, since everything is based on Palatini, if anybody has tried to add also the Holst term to the Palatini action here, and if this gives anything interesting.
Okay. Thank you very much. Yes, yes, we tried that. We actually have a series of papers which describes these different types of attempts. So the most general setup which I think is kind of interesting is the following. Okay, Palatini gravity is also some particular case of a more general theory, which is Einstein-Cartan theory. Okay, so in Einstein-Cartan theory, what you do is that, so this is basically the gauging of the Lorentz group. So what you have there, you have different variables. One is the gauge field associated with the Lorentz group. Another one is tetrad or the metric, and then you can construct all different types of Lagrangian, in particular that which you mentioned with the Holst term. There are other terms, and this class of theories happens to be very interesting, essentially. So we looked at inflation in this theory. And then there are different regimes, which in some of these regimes, you may get sufficiently much generation of gravitational waves, which is absent in Palatini gravity. Yeah, so yes, that's an interesting.
But the reason I was asking is that then you get a theory that has the Lorentzian path integral well defined, so you don't have the problem that you were mentioning before regarding having.
Yeah, here the trouble is that indeed we can write Lorentzian path integral, but to look at tunneling with the Lorentzian path integral is a complicated task, which would require finding the complex solution of equations of motion. And even in the simple cases, I mean, even if you try to do that in one-dimensional quantum mechanics, then this is just technically complicated. Okay, in quantum mechanics, it's doable, it's complicated, but how to do that in this field theory setup, I don't know. Yeah, complicated.
So the last question from Norma still.
A short question. here. Do you really, in this part, I mean, besides or independently of this model, do you really think that there are no heavy particles or super heavy particles, in particular nearby Planck scale or even grand unification? And
I regret to say,
or is just I mean a framework.
no, I think, yeah, the arguments which I'm putting against heavy particles is related to this issue of naturalness and cancellation of different corrections. So if we are, you see, I mean, what I think, okay. So if you have field theory, really field theory which we understand, normalizable field theory, then if we have two different scales, then we see that the large scale want to bring the small scale to the high value, unless you do different efforts such as supersymmetry or composite Higgs or whatever. So if you don't do these efforts, then to have two scales, two separate scales in field theory is not good. Okay, and that's for me this is a serious problem. There are two ways to solve this problem. There is a way to say that there is SUSY or composite Higgs, and there is another way to say that there are no such particles, and I prefer the second way.
In any case,
It's simpler, and moreover, it looks to be that this is an experimentally, that's where experimental experiment is pushing us.
well, in the accelerators, but in nature it could be. I mean, we don't know, and in particular,
we don't know. But if I say, okay, new physics from this type of arguments was first expected to be found at lab, it didn't happen. It was expected to be found at LHC, this didn't happen.
yes, I completely agree, and that is why looking at other laboratories as the early universe and other these energies cannot be forbidden, said.
Yeah.
So
no, it's not forbidden.
And even supersymmetry, even supersymmetry. Of course, the fact that it has not been found is because it's not. It could be, and as the hints appear, that is not the LHC, the energy for the scale of the breaking of supersymmetry, but it's the grand unification scale. There are hints for that. So I think that nature is more than, I mean, is more than a framework. And so, in particular, for instance, from other theories, as said, string theories or quantum gravity theories in different waves, towers of massive powers of massive particles cannot be forbidden. So it could be, of course, it could be that then the case, of course, but even from very early quantum fluctuations, it could appear quantum fluctuation and the Planck scales, and so really it could be so narrow, set from the point of view of physics, to think in the physics ends at the standard model of particle physics.
Yeah, well, of course.
Even for grand unification, I mean, a little bit surprised, it said that.
I mean, of course, we don't know what happens at high energies, and we are making different hypotheses. Which hypothesis will happen to be true, or which hypothesis will happen to be wrong. We don't know, right? That depends on different experiments, and also from theoretical side, that depends on the way the final theory is presented. So at the moment, we are searching for this hypothesis, different hypothesis, and we don't know what will happen, what the eventual theory will be. Okay. So what I'm trying to say is that I want to do that kind of step by step, if you want. So starting from something which is simple and adding new ingredients when they are required by experiment or by development of the theory.
Okay, I have to close this session. So thanks, Misha, again for very nice talk. And